Hi and welcome to Tutorial 7. In this tutorial, we're going to review Assignment 1, including by reviewing the model building process and providing some tips and guidance for the write-up portion as you proceed with Assignment 2. Remember that interpretations of coefficients with linear regression should refer to the change in the mean of the outcome. This is in contrast with logistic regression, where these refer to the change in the log odds of the outcome. You should always be clear about the groups compared, units of measurement, and variables that have been adjusted for when interpreting coefficients. For example, men have a salary that is an average of $2,000 higher than women, adjusting for years since degree was obtained and degree type. Also, remember to interpret confidence intervals in a sentence. For example, we are 95% confident that men have a mean salary that is between $200 and $3,000 higher than women, adjusting for years since degree and degree. You should also list the variables included in the model when interpreting the R-squared. For example, if the R-squared is 0.5, you would say that 50% of the variation in salary can be explained by sex, degree, and years since degree. This is just a quick review of nested model comparisons. First, let's talk about the situation without interaction terms, like when you were asked if years since degree or degree should be added to the model in Assignment 1. When you're asked if a variable should be included in a model, in addition to theoretical considerations and examining bivariate associations between the new variable and the primary explanatory and outcome variables, you should also do these model comparisons. So first, you should look at the change in the coefficient and standard error of the primary variable when the new variable is added, comparing the nested model without the variable to the full model that includes the new variable. If there's a 10% change in beta 1, which was for gender on Assignment 1, this suggests that the new variable is a confounder. Remember, though, that with logistic regression, although we are interested in the change of the coefficient, we are more interested in if the variable meets the traditional definition of a confounder, theoretically and with bivariate associations with the primary explanatory and outcome variable. And this is because we're working with logs. Examining the change in the coefficient is still informative with logistic regression, but we need to rely more on the variable meeting the definition of a confounder, so being associated with the primary explanatory variable and being a predictor of the outcome, but not on the causal pathway. We should also look at the change in the standard error for beta 1 when we add a variable to the model. If the standard error decreases without a 10% change in beta 1, this suggests the variable is a predictor. A large increase in the standard error suggests that the new variable is collinear with your primary explanatory variable. You should also conduct a partial F-test to compare the nested and full model, or a likelihood ratio test in the case of logistic regression. If the partial F-test is significant, so the sum of squared error is reduced with the addition of a variable, this means that adding the variable has improved the predictive power of the model. The full model is better. You could also use the AIC or BIC, which can be used with both nested and non-nested models. Like a significant partial F-test, a lower AIC or BIC with the addition of a variable suggests that this new variable improves the model predictive power or makes the model better. If the variable was not found to be a confounder, but the partial F-test was significant or the AIC was lower, this suggests the variable is another predictor of the outcome. Some people talk about looking at the R-squared when determining whether or not a variable should be added to a model. If the R-squared increases with the addition of a variable, this suggests that more variability in the outcome is explained by including the variable in the model. However, as I've mentioned in past tutorials, I wouldn't rely too much on the R-squared change for deciding whether or not to include a variable. The R-squared will always increase when we add more variables, so we shouldn't compare the R-squares of models to determine which fit is better. Also, the R-squared is how the model predicts the data, but we use the data to predict the model, so it doesn't really make sense to use this to compare models. The important thing is that once you've taken all these steps, you need to say which results have led you to decide to include or not include the variable in your model. If you call a variable a confounder, make sure to explicitly state why you think it's a confounder and that you have therefore decided to include the variable in the model to adjust for its confounding effect. The same is true of predictors. In assignment 1, some people did the right analyses, but then didn't make it clear if or why they thought a variable was a predictor. So you need to be clear that a decrease in the gender standard error, or an improvement in the predictive power based on a partial f-test, or a lower AIC without a 10% change in beta 1, suggests that the variable is a predictor. And then you need to decide and justify whether you should keep the variable in your model. Remember that one important reason to keep a predictor in is that it improves the precision of the effect of your primary explanatory variable on the outcome. But you may also decide that it's not necessary to adjust for it if it doesn't meet the diagnostic criteria of a confounder, or because you want to avoid overfitting. Either way, you just need to be clear about what your choice of whether or not to keep the variable in the model or not is based on. Now we'll turn to model comparisons with interaction terms. To compare a model with an interaction term to a model without an interaction term with linear regression, you can use the partial f-test, since the model without the interaction term is nested within the model with an interaction term. You would use the likelihood ratio test with logistic regression. You can also use the AIC or BIC. If including the interaction term lowers the AIC or BIC of the model, this provides evidence to keep the interaction term in the model. But the partial f-test allows you to assess if an interaction term significantly improves the model predictive power. If this is not significant, you would state that you fail to reject the null hypothesis and have evidence to suggest that the model which includes the interaction term is not significantly better. If this was testing a gender times degree interaction term, you would then conclude that the result suggests that the effect of gender on salary is not modified by degree type, and so this interaction term should not be kept in the model. If the interaction term is significant, you should proceed with the full model that includes the interaction term, because the model is significantly better. So allowing the effect of the explanatory variable of interest to vary according to the effect modifier fits the data better than not allowing it to do so. As a side note, remember that the partial f-test is different than the f-statistic that is provided in your regression model output. This f-statistic in your model output tells you the overall model significance. It answers the question, is the model better than nothing? It's not very informative. In contrast, the partial f-test runs ANOVA to compare the f-statistic of two models to see if the sum of squared error is reduced when we add a variable. It answers the question, does adding the variable make the model better? Just a reminder about checking interaction terms. You always add the interaction term to your last model that you've accepted as being your best model. And those are the two models compared. The model with the interaction term is the full model, and the model without the interaction term is the nested model. So in assignment 1, Mike had indicated that the model including gender, years since degree, and degree should be the model you use regardless of the decisions you made about which variables to keep in the previous questions. So you would compare this model to a new model that tests sex times years since degree, but also keeps the covariates from the previous model in. So this is our full model. This is just another reminder about hypothesis testing. Whenever you're asked to conduct a hypothesis test, such as a two-sample t-test or linear regression, to examine an association between variables, you should always state the null and alternative hypotheses, as well as list and check all of the relevant assumptions. Remember that based on a hypothesis test, we are not proving the null or alternative hypothesis. Instead, we either reject or fail to reject the null hypothesis. Another thing with the assignments is that some of you listed the regression assumptions, but didn't fully explain how you checked these. To check the linearity and constant variance assumptions, we reviewed the residuals versus fitted plot. With linearity, If there is no pattern to the residuals plotted against the fitted values, and there is a fitted flat red line, this assumption is met. You can see here in the plot on the left from the assignment, the line is fairly flat, suggesting that the linearity assumption is met. Conversely, in the plot on the right from another data set, there is a non-linear relationship. The line is not flat. As for constant variance, if there is no pattern to the residuals plotted against the fitted values, this assumption is met. You want the cloud of points to be constant around the line. On the left plot, you can see that the variance seems to increase as salary increases. There's a megaphone pattern. On the right, it's really hard to assess the variance because the linearity assumption is violated. So we'd want to address the linearity assumption first, and then check the variance again to see if the issue was addressed. We use the QQ plot to check normality. The plot on the left is from assignment 1. The line generally follows a straight diagonal line, suggesting the normality assumption is approximately met. And remember that normality is probably the least concerning assumption to violate, especially if you have a large sample size. But with the plot on the right, you can see that the line curves and does not follow a straight diagonal pattern we want to see. So this assumption is violated here. These are just some general tips as you proceed with your assignments. The first is to remember to read the questions carefully. So some of you had perfect answers for most of a question, but then didn't address a specific sub-question that was asked. For example, whether or not a variable should be kept in a model. So you did all the right analyses, but then didn't use these to justify a decision for keeping or dropping the variable. Another example is that some people checked all regression assumptions, but then didn't answer the question about how violations could be potentially addressed. Another tip is to only include what's relevant in your answers. You need to be selective and only include what you think is necessary or important to answer the question asked. For example, if a question asks about the effect of gender on salary, you don't need to interpret the coefficients for the other variables that you've included in your model. A final tip is to justify your decisions. I've already talked about this with confounders and predictors, but whenever you make a decision, you need to make an explicit link to the findings that led you to this decision. So don't expect that we'll understand which part of the findings that you've discussed led you to this decision. So now let's turn to the write-up portion. As you'll know, there's a grading rubric for this on Connect that provides information about what we're looking for when we mark these. For the introduction, there's no need to conduct a literature review. You want a few sentences to provide a rationale and clear statement of the objective of the analysis. An example objective for assignment 1 could be, the aim of this study was to determine if a difference in salary between males and females exists when controlling for potential confounders. The methods and the results are the parts of the write-up that are the most heavily weighted, as you can see in the marking rubric. This is not an exhaustive list of what should be included. There may be other things that should be included depending on your research question and the analyses conducted. This is more of a set of guidelines to help you determine what you should include in your write-up. So you want to describe the study based on the available information. This includes descriptions of things like the setting, participants, sample size, study design, and the measurement of variables that are included in your analyses. There should be no results in the methods section. You also want to describe your analytic approach, including descriptive, bivariate, and multivariate analyses. Importantly, you want to include the criteria that you use to decide which variables to keep or drop from your multivariable model. So, are you only keeping in variables that meet the definition of a confounder or predictors too? How are you defining confounders and predictors? Based on what you say in your methods, only variables that meet your definitions should be included in your final model. Other aspects of the analytic approach that you want to discuss are, what methods are you using to assess effect modification? Remember that this should make sense theoretically. Also, how are you assessing assumptions for hypothesis tests, and which software did you use? So here's an example write-up for the methods. I won't read this out because you can review this in your slides, but you can see that this provides a description of the study and variables assessed. This is an example of the analytic approach section of the methods. This includes exploratory descriptive analyses as well as bivariable and multivariable analyses. This describes the multivariable model building process, including variable selection criteria and methods for assessing effect modification and model assumptions. When writing the results section, there should be no results included that were not described in the methods. Do not interpret your findings in the results. This should be reserved for the discussion, so you should simply state what you found. There is no need to report all exploratory data analyses. Only include those that are the most important or relevant. At the very least, you should report descriptive statistics for your primary explanatory and outcome variables. But you could also include important bivariable analyses. There's also no need to report all models that you fit. We only had 3 models in assignment 1, so you don't need to present the results of each model. You have done the work in fitting the best model using the methods that you've described, so your job is to report the findings to the reader. So you can just describe the simple linear regression results and the final multivariable model results, not each step of model building. And you should also indicate if and why certain variables were retained in the final model. Also, there's no need to discuss the effects of secondary explanatory variables in your results with an effect size model. For example, with assignment 1, we were interested in the association between gender and salary. So there's no need to report the coefficient for degree or years since degree in your write-up, although you could present the multivariable results as a table. So now let's turn to what you should include in your results section. Again, this is not an exhaustive list of what to include and may change depending on your research question and the analyses that you conduct. But it's more of a general guide about what you should address in your write-up. First, you want to describe your overall sample. This includes descriptive statistics for the primary explanatory and outcome variables at the very least. You might want to include a table of descriptives for your variables. You also want to report the unadjusted association between your primary explanatory variable and the outcome. Another thing to mention is which other explanatory variables were retained in your model and why. Did these meet the definition of a confounder or a predictor? Your decisions about which confounders, predictors, or effect modifiers to include should match the plan you outlined in your methods. There's no need to repeat your definition or assessment of confounders, predictors, or effect modifiers in the results. You should also report the adjusted effect of your primary explanatory variable from your final model. Remember though, if we decide to keep an interaction term in the model, it doesn't make sense to interpret the coefficient of the primary explanatory variable on its own. For example, let's say that in assignment 1, we found that the interaction term between gender and degree was significant. We didn't, but let's say that we did. This suggests that the effect of gender on salary depends on the type of degree that you have. The effect of gender is modified depending on what type of degree you have. So it doesn't make sense to interpret the effect of gender on salary without considering degree. Anything you say about the effect of gender on salary has to be specific to the degree you have, because we've determined that the effect of gender on salary is degree specific. Finally, you should indicate if your assumptions are met. There should be no need to get into much detail here, because you've already outlined how you assessed assumptions in the methods. For the discussion section, you want to include a summary of your key findings. There's no need to detail exact test statistics or describe your full analytic approach. You want to be selective about summarizing only what you believe to be the most important results, and no new results should be brought up in the discussion. You definitely want to include the effect of your primary explanatory variable on the outcome, particularly from your final model. If you find that the effect of your explanatory variable is modified by another variable, you should focus on that finding. You then want to provide a short interpretation of your key findings, including possible explanations and why this matters in the broader picture. And you also want to mention your main study limitations. Finally, remember that some marks are allocated to presentation and flow, including clarity, logical development of ideas, only including relevant information, neat tables and figures, following guidelines, accurate use of terms and symbols, lack of errors, and attention to detail. In the next tutorial, we're going to wrap up logistic regression. We'll review why we use the logit link and how to calculate and interpret odds ratios when you have one or two interaction terms in your model. We'll also discuss the Mantel-Hansel method and how to check linearity with logistic regression.
Thanks for watching our video. Stick around, guys, because we got lots more.